We will wait for a few more minutes so that students, if someone they are joining, they can join, and then we will start at 7:10. Hello everyone, a very good evening to all. Myself, Vivekananda Nayak. I am a PhD research scholar in the Department of Energy Science and Engineering, IIT Delhi. I welcome you all once again for this seventh interaction session on the course Atomic and Molecular Physics being flowed by NPTEL this January 2026 session with course code NOC 26 PH18. Now, since this is our seventh interaction session, we will be solving a few sample problems that will be based on week 6 lectures of the course. So first we will briefly discuss about the concepts covered in this week's lecture, that is lecture number 31 to lecture number 35, which is week 7 course content, and then we will solve a few sample problems based on those concepts. So let's start our discussion. So if you talk about week 7 lectures, so week 7 lecture was mainly about quantum mechanical treatment of hydrogen atom, which we started in the last interaction session. So it was quantum mechanical treatment of hydrogen atom. So we know in case of hydrogen atom, it has a single electron which is revolving around the nucleus, and the nucleus contains only one proton. So in order to solve it quantum mechanically, we need to solve the Schrodinger's wave equation. The Schrodinger's wave equation is nothing but H psi equals to E psi, where H is kinetic energy plus potential energy. So if you write it, it will be minus h cross square by 2m del square psi plus v psi equals to E psi. But now the question arises, psi is a function of position coordinates. So for time independent Schrodinger equation, it is function of only positions. But if you see, in case of hydrogen atom, if you talk about the system of hydrogen atom, so it has one proton at the nucleus and one electron. It is revolving around the nucleus in an elliptical, in an orbit. So here we need to consider the reduced mass of the system. So the reduced mass of the system can be written as mu equals to me mp divided by me plus mp. And now what is the value of the potential? So the potential, we know it is a coulombic repulsive, sorry, it is a coulomb potential. So the potential is attractive nature, and the form of the potential is minus e square by 4 pi epsilon 0 r. So now if you see, the potential is a function of r only. So if you talk about the Cartesian coordinates and the relation with spherical polar coordinates, so r will be x square plus y square plus z square root. And unless we if suppose we are taking the wave equation, sorry, we are taking the wave function as the function of x, y and z, then it will be quite difficult for us, because unless we separate the variables x, y and z and solve the equations separately, then only we can get the solution. And if we are converting r to xyz, that is from spherical polar coordinates to Cartesian coordinates, then it will be quite difficult for us for variable separation. So what we will do, we will solve the Schrodinger wave equation in spherical polar coordinates itself. So if we are solving the wave equation, then what will be the wave equation? So in spherical polar coordinates, the wave equation will be minus h cross square by 2m, sorry, 2 mu. We can write m as mu. Then del square psi r theta phi plus v function of r psi r theta phi equals to e psi r theta phi, where what is the form of del square operator? It is 1 by r square del by del r of r square del by del r plus 1 by r square sin theta del by del theta of sin theta del by del theta plus 1 by r square sin square theta del square by del phi square. And then we will write the wave function which is a function of r theta phi as r theta, which is a function of theta, and phi, which is a function of phi, and then we can solve it separately. So if you very simply we can if we discuss, so this phi component, it can be written as d square phi by d phi square plus ml square phi equals to 0. And if you talk about its solution, we had discussed in the previous interactions also, the solution will be of the form a e to the power plus minus I ml phi, where if you talk about the normalization constant a will be 1 by 2 pi root over, because phi it has limits 0 to 2 pi. So we can so similarly we can solve for r part and theta part, and then we can get the actual wave function. So the if you see, for example, the ground state wave function, which is psi 100, it can be written as 1 by pi a0 q root over e to the power minus r by a0, where n is 1, l is 0, and m is 0, and a0 is Bohr's radius. Also, towards the end lectures, like lecture 34 and 35, some concept regarding orbital angular momentum operator was also discussed. Orbital angular momentum operator. So we know orbital angular momentum L vector can be written as r vector cross p vector. So if we know for p vector, it is represented by minus I h cross del by del x. So with this, if we solve it, so we can get Lx, it is minus I h cross. So Lx cap we can write minus I h cross y del by del z minus z del by del y. Ly cap is minus I h cross z del by del x minus x del by del z, and Lz cap is minus I h cross x del by del y minus y del by del x. And we can write L square is equals to Lx square plus Ly square plus Lz square. And also some we can write Lz as minus I h cross del by del phi, and L square we can write as minus h cross square taken as common. It will be 1 by sin theta del by del theta sin theta del by del theta plus 1 by sin square theta del square by del phi square. Also, some concepts regarding commutator algebra was also discussed. So commutator algebra, which is AB, we can write it as minus BA. So AB is basically AB minus B. A cap B cap minus B cap A cap. Similarly, if we calculate the commutator of X Px, it will come out to be IH cross. So these are the concepts that was covered in these 6 lectures. So now let's start solving the problems that are based on these concepts. So let's discuss question number 1. So question number 1 says 3 sets of principal angular momentum and magnetic quantum numbers are given for hydrogen like atom. Set 1, n equal to 1, l equal to 0, m equal to 0. Set 2, n equal to 2, l equal to 0, m equal to 0, or set 3, n equal to 2, l equal to 1, and m equal to 0. And the question says for which set or sets the wave function of hydrogen like atom will depend upon the polar coordinate theta. So out of these 3 cases, set 1, set 2, and set 3, in which of the cases, or it may be one or more than one cases, the wave function will be a function of theta. The options are option A, set 2 and 3, option B, only set 3, option C, set 1 and set 3, and option D, only set 2. So these are the 4 options. I'll give you a few minutes. Depending upon the concepts that we have already briefly discussed, we will solve the question then. First, you try to solve it to get the correct answer, and then we will discuss. So, um, so we already discussed. So, in order to solve the coordinate system equation, you need to do the variable separation. So, after separation of variable, if we solve, we will get the wave function as n, l, and m. So it will be a different forms. Now, if you talk about the cases, so here case one is n equal to 1, l equal to 0, and m equals to 0. So it is psi 100. So psi 100, as we have already discussed, it is 1 by pi a0 q root over e to the power minus r by a0. Again, this is not depending upon the polar coordinate theta. So now let's evaluate psi 200. So psi 200 is equals to 1 by 32 pi a0 cube square root 2 minus r by a0 r by 2 a0. Again, this is independent of theta. And now we move to, this is case 2 and then case 3. So case 3 is n equal to 2, l equal to 1, m equal to 0. So 2, 1, 0. So when l is non-zero, then we will be having theta component, because theta component is mainly related to l and phi component is mainly related to m. So it will be 1 by 32 pi a0 cube root over r by a0 e to the power minus r by 2a0 cos theta. So here we have we are having the dependency of theta. What is a0? So a0 is Bohr's radius. So and r is the radial variable and theta is the spherical variable. So in the case where n equal to 2, l equal to 1, and m equal to 0, in that case only the wave function will be having theta dependence. So the correct option will be only set 3, that is option B. In case of set 3 only, when l is non-zero, we will be having the dependency of wave function on theta. With this, we come to the second question. The question says, if electron spin degeneracy is not considered, then the hydrogen atom energy levels in its nth state are dash fold degenerate, where n is the principal quantum number. Options are option A n, option B 2n, option C n square, or option D 2n minus 1. So here the question says, if we didn't consider the contribution of spin, then what will be the degeneracy of the hydrogen atom energy levels in nth state? We don't need to consider the electron spin degeneracy. So I'll give you a few minutes and then we will calculate what will be the degeneracy of the electron energy levels if we don't consider the spin. Because if we are considering the spin, then according to the spin, we know since electron is a spin of particle, so degeneracy is 2s plus 1, that is 2. But here, if we are not considering, then what will be the degeneracy of the energy levels, that we need to find out. So now if we solve it, we know the value of n starts from 1 and these are in positive integers 1 to 3 like that, and for each n, L is 0 to n minus 1, that is 0, 1, 2 up to n minus 1, and corresponding to each L we have ml values where it is 0 plus minus 1 plus minus 2, that is 2L plus 1 values. So how we will calculate the degeneracy? So the degeneracy of nth state, it will be Gn, and it is integration of L 0 to n minus 1, it will be 2L plus 1 values. So now you see, if we, so L is 0 to n minus 1, again L, for a particular value of n, L will be having n number of values. For example, suppose n is 3, then what are the value of L? L is 0, 1, 2, and this is again 3 values. So if we see the summation, then for each L we will be having 1. So here, since L is 0 to n minus 1 means we need to add it by n times. So n times means it will be 2L integration. What we can write? We can write L equals to 0 to n minus 1 2L plus n, because n times 1 will be added, so it will be this much. So now what will be the value of the summation? We know, so from 1 plus 2 plus 3 up to n is given by n into n plus 1 by 2, isn't it? So here 2 will take as common, and then it will be L is equals to 0 to n minus 1 2L plus n. Now 2, and here you can see it is 0 to n minus 1. So the formula n into n plus 1, here n is n minus 1. So it will be n minus 1 into n divided by 2 plus n. So 2 2 gets cancelled out. So now it becomes Gn is n minus 1 into n plus n. So it is n square minus n plus n, and it is n square. So here you see we have not considered the spin degeneracy. If we would have considered the spin degeneracy, then additional 2 will be coming here, because due to spin, each state will be having doublets, that is spin half means 12 plus 1 multiplicity will become 2s plus 1 multiplicity will become 2. So the correct option will be, correct answer will be n square, and the correct option is option C, that is n square. I hope this is clear to everyone. Now we'll move to question number 3. So question number 3 says the probability of finding the electron between the distance r and r plus dr in ground state of hydrogen atom is, options are option A 4r square by a0 cube e to the power 2r by a0, option B 4r square by a0 cube e to the power minus 2r by a0 dr, option C r square by a0 cube e to the power minus r by a0, or option D 4r by a0 square e to the power minus 2r by a0. So these are the 4 options, and we need to find out what will be the probability of finding the electron between the distance r and r plus dr. So I'll give you a few minutes and then we will calculate. So we know the wave function has no physical significance, but if we want to find out the probability of finding the particle, then it is represented by the mod of the square of the mod of the wave function. So we know the probability. So the probability of finding the particle between r and r plus dr, it is given as psi mod square dr, where now if you consider the total volume, sorry, it is, so the total volume, then we need to take the integration. So the volume, we know volume is given as 4 pi r square into dr. So between r and r plus dr means the volume it will cover is 4 pi r square into dr. So now if we are taking the integration, so it should be taken over whole range of theta and phi, but here we only take the range dr. So it will be psi mod square dr into integration over theta and phi component d theta d phi, and this is total 4 pi. So this is 4 pi r square. If you take the integration, so it will be coming out to be, so this is psi mod square dr into 4 pi r square. Now what is psi? Psi 100. So psi 100 is given by 1 by pi a0 cube root over e to the power minus r by a0. Then the probability density will be psi mod square dr into 4 pi r square. So it will be 1 by pi a0 cube e to the power minus 2r by a0 into 4 pi r square into dr. So if you solve it, pi will get cancelled out. There will be 4 r square by a0 cube. So it will be 4 r square divided by a0 cube e to the power minus 2r by a0 into dr. This is the probability. So the correct option will be 4r square by a0 cube e to the power minus 2r by a0 into dr. So the correct option will be option B. Now we move to question number 4. Question number 4 says the nature of variation of probability distribution function PR for ground state of hydrogen atom is. So there are three figures, figure 1, figure 2 and figure 3, and we need to find out what will be the correct options. Options are option A figure 1, option B figure 2, option C figure 3, or option D none of the above figures. So I'll give you a few minutes. So it is similar to the previous question that we discussed, and we need to find out what will be the correct option. So if we solve it, so in the previous question we solved the probability of the probability distribution function for ground state is 4 r square by a0 cube e to the power minus 2 r by a0. So if we, this is the probability distribution function. So if you compare it with the variation, so at r equals to 0, so if you see the nature of this wave function, so it will be like this figure 3. So it will first go on increasing, and then after r equals to a0 it will fall. So the correct option will be option C, that is figure 3. Now I move to question number 5. Question number 5 says the normalized wave function of hydrogen atom for principal quantum number n equal to 1, the angular momentum quantum number L equal to 0, and the magnetic quantum number m equal to 0 is, options are option A psi r theta phi. So these are the four options. So since the options are quite long, so I am not going to read the options one by one. So these are the four options, and we need to find out what will be the normalized wave function of hydrogen atom for principal quantum number n equal to 1, L equal to 0, and m equal to 0. So I'll give you a few minutes and then we will discuss. So actually, if you look at the options, the question there is some printing mistake. Actually, it should be n equals to 2, l equal to 1, and m equal to 0, because we have already discussed for psi 100 it is 1 by pi a0 q root over e to the power minus r by a0. So now if we discuss this for 210, so what will be psi 210? So the question should be like this. So we know we write psi nlm, which is a function of r, theta and phi, as r, which is a function of n and l, r, then y lm, theta, phi. This is called as spherical harmonics. So for n equals to 2, l equal to 1, and m equal to 0, what will be the form? So it is 2p state. Basically it is 2p state. So 2px, 2py, 2pz. So 2pz is 210, so 2pz state. So 2px will be 211, 2py will be 21 minus 1. So what will be the form? So psi 210 will be 1 by 4 into 2 pi a0 cube root over r by a0 e to the power minus r by 2a0 cos theta. So if you match it with the options, so option B will be the correct option. 1 by 4 2 pi a0 q to the power root r by a0 e to the power minus r by 2a0 cos theta. So the correct option will be option B. So more details in this regard, it has been discussed in the course lectures how the forms are being, because if you try to evaluate the wave functions or the solutions of the wave equation, then we will be having energy agent values and agent functions. So like for n1 we have only one wave function, that is psi 100. So for n equal to 1 we have only one, which is psi 100, but for n equal to 2 we have 4 states, because we discussed for n the degeneracy is n square. So 4 means psi 200, psi 210, psi 211, psi 21 minus 1. So these are 4 levels or 4 states which have same energy, because n is same for all of them, but the wave functions are different depending upon the values of l and m. So these are they are expressed in terms of different functions like Legendre polynomial, Lagrange polynomial. All these things has been discussed in the course lectures while solving the Schrödinger's wave equation. I hope you must have gone through the lecture, so it will be quite helpful for you to solve this problem. So the correct option here will be B, depending upon the concepts covered. Now question number 6. Question number 6 says the nature of variation of the radial wave function for principal quantum number n equal to 1 and angular momentum quantum number l equal to 0 is like. So as we already discussed, so it is RNL. So RNL means here the options are given: figure 1, figure 2, figure 3, and figure 4, and we need to find out R10. So what will be the expression? First we need to find out what will be the expression for R10, and then we will compare it with the graphs present to find out what will be the correct graphical representation of the function R10. You should keep in mind R10, it is not equal to psi 100 because r10 into y00, so psi 100 is r10 into y00. So we need to find out r10 and then we can get the correct answer. So I'll give you a few minutes and then we will discuss. So if we discuss about the expression for R10, so in general, what is the expression for RNL? So RNL, which is a function of R only, it is 2 by NA0 to the power 3 by 2, then N minus L minus 1, then 2N into N plus L, then 2R by NA0 to the power L e to the power minus R by NA0, then L 2L plus 1 N minus L minus 1 2R by NA0, where this L is associated Laguerre polynomial. So now if we talk about the radial function R10, then N equal to 1, L equal to 0. So if you put the values, then here L 2L plus 1, it will be 1, and N minus L minus 1, it will be 0. So L x 0 1, it is 1 only. So if you put all the values, R10 function of R, it will be 2 by A0 to the power 3 by 2 e to the power minus R by A0, or we can write it as 2 sorry, this is 1 by A0 to the power, so this is 2 will be outside, so 2 A0 to the power minus 3 by 2 e to the power minus R by A0. So now you should be keeping in mind that the function, the form of psi 100 was different from this. So now if we see the wave function, so it is minus R by A0, so it is decays exponentially, and the figure that shows exponentially decaying nature, this is the expression. So it is exponentially decaying. So at r equals to 0, it has maximum value, and then it decays exponentially with increasing value of r. So it is figure 1 shows the same trend. So the correct option will be option A, that is figure 1. Now we move to question number 7. So question number 7 says, if RNL, which is a function of R, is the radial wave function of hydrogen atom, where N and L are, let me first, so if RNL is the radial wave function of hydrogen atom, where N and L are principal and angular momentum quantum numbers respectively, then the radial probability density PNLR is given by, so we have already discussed it. So the radial probability density PLNR, it will be given by R square and mod square of RNL. So we had already discussed, it will be R square RNL mod square. The PNLR is equals to R square RNL mod square. So the correct option is option C. So it is a standard information, a standard formula that has been discussed in the lecture content of the week. Now we move to question number 8. Question number 8 says, the spherical harmonics part, that is the angular part of the wave function of hydrogen atom, for L equal to 2 and M equal to 0. will be y nl theta phi is equals to, the options are option A 5 by 6 pi root over 2 cos square theta minus 1, option B 5 by 16 pi root over 3 cos square theta minus 1, option C 3 by pi root over 2 cos theta minus 1, or option D 1 by pi root over 3 cos theta minus 2 sin theta. So these are the four options, and we need to find out the correct expression for. So we discussed it is y lm theta phi. So here m is 0, l is 2, and we need to find out the expression for y lm. So I'll give a few minutes and then we will discuss. So if we discuss what is the generalized formula for YLM, so YLM theta phi, it is equals to 2L plus 1 by 4 pi L minus m factorial divided by L plus m factorial root over PLM cos theta e to the power Im phi. So here this PLM cos theta is called as associated legendary polynomial. Associated legendary polynomial. So if you put the values, then what will be the expression for y20? So y20 will be y20 theta phi. It will be 5 by 16 pi root over. So you can calculate this 12 plus 1. 12 plus 1 is 5. So 5 by 4 pi. And this is L minus m. L minus m is 2 factorial. L plus m is 2 factorial. 2 factorial by 2 factorial. So it was 5 by 16 pi. And then e to the power 0, it will be 1 only. And PLM cos phi for associated legendary polynomial, it will be 3 cos square theta minus 1. So y20 will be 5 divided by 16 pi root over 3 cos square theta minus 1. So the correct answer is option B, 3 cos square theta minus 1. Now we move to question number 9. Question number 9 says the y component, that is Ly, of angular momentum vector L vector, where r vector is the position vector and p vector is the linear momentum vector, then what will be the expression for Ly? Option A, y pz minus z py. Option B, x py minus y px. Option C, z px minus x pz. Or option D, y py minus x px. So these are the four options. I'll give you a few minutes and then we will discuss what will be the correct answer. So we know the expression for L vector is R vector cross P vector. So it is I cap, J cap, K cap, X, Y, Z, P X, P Y, P Z. So if we solve it, so L vector can be written as I cap Lx plus J cap Ly plus K cap Lz. So it is I cap Y Pz minus Z Py, I cap Y Pz minus Z Py minus J cap X Pz minus Z Px, X Pz minus Z Px plus K cap Y X Py minus Y Px, X Py minus Y Px. So if we write it, it will be I cap Y Pz minus Z Py plus J cap Z Px minus X Pz plus K cap X Py minus Y Px. So if you compare it with Ly, so Z Px minus X Pz will be Ly. So Ly will be Z Px minus X Pz. So the correct answer is option C, Z Px minus X Pz. I hope this is clear to everyone. Now we'll move to question number 10. The question number 10 says the nature of variation of the potential energy of an electron in hydrogen atom with distance r from the nucleus is like. These are the four figures: figure 1, figure 2, figure 3, and figure 4. And we need to find out what will be the correct option. Option A is figure 1, option B is figure 2, option C is figure 3, and option D is figure 4. And it says the nature of variation of the potential energy of an electron in hydrogen atom. So we know the form of the potential U, which is a function of R. Then we need to first find out the mathematical form, and then we can convert it into the graphical form. So I'll give you a few minutes, and then we'll discuss what will be the correct answer. So if we solve it, we know uh, the potential energy of an electron in hydrogen atom. It is given by the expression UR is minus 1 by 4 pi epsilon 0 R. So it varies as 1 by R, and it is in negative quadrant. So now let's, so UR, it is direct proportional to 1 by R and it is negative. So um, let's consider the graphical representation. So negative means for positive value of R it will be negative. So it will be in this quadrant only, Q1, Q2, Q3, Q4, this quadrant only. So now suppose let's only discuss about 1 by R. So there is a function which is fx is 1 by x. This is R only, and this is u, which is a function of R. So when x is equals to 1, fx is 1. When x is 2, fx is 1 by 2. When x is 0.5, fx is 2. So it will cross 1 1, and then so it is negative, so it will be, so it will minus 1 by x, so it will minus 1, minus 1 by 2, and minus 2. So when x equal to 2, x equal to 2, then it will be less than 1, that is minus 1 by 2, it will be here. And when x is less than 1, it will be greater than 1, so it will be somewhat here. So the nature will be like this. So it is the form of 1 by x. So now if you see the options, option 4, it has this form, 1 by x form. So the correct option is figure 4, that is option D. So it is always negative, and when r tends to infinity it becomes 0. So this is the, so when r tends to infinity ur becomes 0. So with this we come to the end of today's interaction session. uh, mm, I hope the problems that I have discussed will definitely help you in solving the course assignments, and as well as if you are preparing for your exams. With this, I hope it will definitely help you in your exam preparations. That's it from my side. Thank you.